Professor Wharton is with us this evening to discuss the physics of time travel. Let's give it up.
Okay, thank you very much. Let's open this. Okay. Let's see if this is starting. Okay, let's start this up. Okay. Went the wrong way. There it goes. That comes later. Or earlier, depending on your perspective. Okay, well, nice big turnout tonight to hear about physics versus time travel, how I termed it. And I guess the burning question then is this going to happen? Is it physically possible? And I'll start out with the good news. And the good news is, as a physicist, I can say absolutely yes. Although I'm only talking here about forward time travel. Now, there are all sorts of ways to forward time travel. From a physicist might say, well, what you need to do, according to relativity, is you get on a spaceship going near the speed of light, which is just an engineering problem, and you go out some amount of time, you come back to Earth, and when you arrive, everyone here will have aged much more than you have yourself, and so you've kind of traveled into the future. But really, we can do that without a light speed spaceship. In fact, we can all do a little experiment here, and here we are in the future. So it's kind of trivial. In fact, it's actually so trivial it's not even meaningful, as we'll talk about, to forward time travel. But the question you're probably here to ask about is backward time travel. That's where the fun stories and movies that I'll be talking about come in. But before we even get to the question of the physics of backward time travel, we have to step back and ask, is this even logically possible? Forget the physics, just is there a coherent logical framework where we can think about backward time travel? And the reason this is tricky is, well, that word, travel. I mean, what does that mean? Well, of course we know what travel means. It means you go some distance over some time. But you notice that time is built into the word travel already. Before you add time, the word time in front of the phrase time travel. And so you kind of have these two different notions of time working together in this time travel story. So you think, well, I know what time travel is. It's obvious. You just move some time over some time instead of a distance over some time. But now you can see here, you do have these two different times here. And so, and it gets even worse. I don't know if you can see this, but I've circled the word move. The word move has time in it as well. And so you quickly get into these weird logical conundrums where you don't even really know how to think about the question, let alone how to answer it. So, as a physicist, we love to frame questions the right way. And so, and then there's more stuff about how if you are traveling at 1 second per second, that's not really very meaningful, right? How fast are you going into the future? Well, you're going at some unitless rate of 1, but you're also going -1 second per -1 second at the exact same time. So it doesn't really mean anything. So we need a framework. We need a framework to think about time. And the way all good physicists think about time, I would say, is this thing called the block universe. So here is something called a space-time diagram. And this purple line here is your world line, according to a physicist's conception. Now I've plotted space as a horizontal axis here, and time as a vertical axis. And there are obviously 3 dimensions of space, and I've suppressed 2 of them here. But you can imagine that this room, the walls of this room, in this dimension anyway, are these red lines, and they're, in our reference frame anyway, not moving, so at every time, they're at the same place. But at one point, you were moving. You came into this room. So at this at this horizontal blue line is the point where you entered the room. And now you're sitting down, or some of you are not moving, and so you're of stationary world lines. And now then you'll, at some point, I imagine, leave the room, and that's your world line. Now, that's a nice way to put all the events in our universe on one diagram. You can think of them in a nice, self-consistent way. But the danger, the mistake you don't want to make is to think that something can change on this diagram. To imagine a little dot moving around, or to imagine any of these lines wiggling, or any sort of change on this diagram is logically impossible because we've already represented time as a spatial axis here. And to have any change, which is very natural to think about change. It's almost hard not to think about change. But if you do think about change on this diagram, you're making a logical blunder because you now have the old version of time that's not a spatial dimension running in the back of your mind. And the careful way to think about this is to freeze everything on the space-time diagram, not let anything change. Now, this bothers a lot of people. This bothers some physicists. To think of everything as this big frozen four-dimensional block. And sometimes people say, but that's not right. Nothing can change in a block universe. But that's not really true. There's still change here. You can see the change on the angles. And I mean, if I gave you a DVD and said, nothing happens in this movie because, look, it's all here in this big stationary thing, you would say, well, that's nonsense. You have to play the DVD, and then you can see what happens. The same thing here. You could take this diagram and play it forward and see the change. The change is all encoded in there. Just because you're looking at a bigger picture doesn't mean that static picture doesn't encode ordinary change. So everything's fine here from a physics perspective. And this is the framework I want to think about time travel in, where it's all one big block universe. And then time travel, well, actually, it's still tricky. So we have to go to beyond physics. We have to go to an even more important reference. Our intrepid ex-governor here, who has taught us the two ways to think about time travel in the first two Terminator movies. And if you haven't seen these for a while or never have, I'll outline the relevant parts. But I'm going to be talking about two different types of time travel stories. The T1 story, from the original Terminator movie, where it's all one big block, consistent universe, just like I described. And other T2 stories, which we're going to try to make sense of as well, where somehow you can change the future or change the past, or depending on how you look at it. It's not all one consistent universe. So let's start with T1, the original and possibly still the best. This is the block universe plot diagram of the first Terminator movie. And the relevant parts of it are that before the movie starts, John Connor sends this guy Reese back in time at the beginning of the movie. So he appears, and during the course of the movie, becomes the father of John Connor, and then later dies. And after he dies after the movie, presumably John Connor is born, and then exists in the future in order to send his father, who doesn't know it, but he sends his father Reese back in time. And meanwhile, the Terminator is destroyed, and we find out in the next movie that they find little pieces from it that inspires the invention of Terminators in the first place. So it's a little bit, and the Terminator, by the way, is sent back in time as well. Okay, so there are all sorts of interesting paradoxes that show up in these T1 type stories. It's all self-consistent, right? There's one big block here. You got space and time. But you have these free will paradoxes. Well, but what if John Connor had decided not to send Reese back in time? Then it's no longer self-consistent. So you almost have to make certain choices to keep things self-consistent. You have these other paradoxes I call bootstrap paradoxes. Like, well, who really did invent the Terminator? If the reason they invented it was because they found pieces from the future, then whoever came up with it in the first place. So you have these various paradoxes in a T1 framework that are interesting and hard to answer questions. There are not very many T1 style movies where it's all one big block universe. They're hard to construct. My favorite and most probably famous example is 12 Monkeys, not the new TV show apparently, which I haven't seen, but I understand it's not T1 anymore. But the original Terry Gilliam movie, there's like a 10-minute scene in the third Harry Potter movie that's all sort of done a T1 style. The Time Traveler's Wife. The one that actually impressed me, disliked it for various other reasons, but they actually kept several seasons of a time travel story going on Lost, all in one big consistent block universe. And then it seemed like in the last season that that wasn't true, but at the very end they revealed that, yes, it really was all one big T1 story. And maybe it's a plot spoiler at this point, but I'll throw Interstellar on the list as well. There are not too many others, because you have to carefully construct these things. And they come up with different solutions to these paradoxes. None of them really address the bootstrap paradox. Interstellar, by the way, has lots of bootstrap paradoxes you can find in Interstellar. But as far as how you solve the free will paradox, you could make it uncontrollable, where you just can't help yourself. You just are time traveling whether you want to or not. Or you deny information to the characters. Or my favorite is when, oh no, we can't do that or we'll destroy the universe. We have to do this, or else there'll be a paradox. And so you get this self-consistency by making the characters fear what would happen if they weren't self-consistent. Or just say, well, there's no free will at all. Oh, that's not a, maybe, that was a movie. I never saw the movie. Anyway, I know the book, Slaughterhouse-Five, which is also kind of in a T1 style. Okay, so that's one style time travel movie, and it's important to keep these separate because they are really, really different. Even though this was actually the sequel, it's still really, really different. And what happened in T2, or all you need to know, is that Arnold now is a good guy. He goes back in time. He's the T-800, and he stops a nuclear war. And he stops a nuclear war that had already happened to him, or in his world. And suddenly now, he's in a universe that has no nuclear war. And the only really logically coherent way to think about this is as another universe, because it's logically incoherent for there to both be a nuclear war at some day and not a nuclear war at some day, right? There's one space and one time. You can't logically have two different things happening at that space and time. So you have to have two different universes to keep track of. Anytime you have a story where you're changing the past, really the only logical way to think about it is, okay, this is a brand new universe. Now, there are all sorts of different ways you could do this. You could perhaps destroy one universe and then launch a new universe. When you travel back in time, you could say, well, they're just always there, and you're just universe jumping. Really, you're not time traveling. You're kind of universe traveling. Or, you know, there's all sorts of interesting combinations you could come up with, some more coherent than others. But the nice thing about this is you don't have any paradoxes. You can go back and kill your grandfather, and that's fine. Your grandfather is not around in this second universe, but he was around in the first one, which is how you got to be there in the first place. You get around all of these paradoxes very easily in a T2 story, which is why many movies and stories are in sort of this T2 framework. Now, the best explanation of how this T2 story works is this infamous chalkboard scene from Back to the Future. I think this is still spoken of in screenwriting schools as something never ever to do. Never put your character in front of a chalkboard explaining things to the audience. But it really, I remember when I first saw it being very confused by it. I think now that I've seen it many times, it's actually very clear and straightforward, but it totally contradicted everything you knew from the first movie. So that's probably why it seemed a little confusing. But here, I think I actually stole it from YouTube here. Let's see if I got the clip.
Imagine that this line represents time. Here's the present, 1985, future, past. Prior to this point in time, somewhere in the past, the timeline skewed into this tangent, creating an alternate 1985. Alternate to you, me, and Einstein. But reality for everyone else.
Okay, the famous Doc Brown's words of wisdom here. Okay, so now the question here is, well, we clearly have time going from left to right, but what is this vertical axis supposed to represent? It's not space. It means some other universe. The first line is one universe, and the bottom line is kind of like this new timeline. You might as well have said a new universe that he just created where something different happened. And so you can't put this kind of story in a four-dimensional block universe. So you need this multiverse kind of story. Okay, is that all, there's T1, there's T2. I don't even know what you would call. Oh yeah. So okay, this was not a very good movie, but there was one interesting point from a time travel perspective, which is that eventually the nuclear war happens. And so yes, you've delayed the nuclear war, but eventually you're sort of fated to have this nuclear war. And yeah, I guess you can imagine that you are now back to the same universe, even though it's sort of inconceivable. If you have a nuclear war a different day, that you end up in the same universe. But nonetheless, you can imagine this sort of thing. Actually, there's a more plausible version of it. I don't know if any of you have read Connie Willis's time travel novels. But to say nothing of the dog is a good one to start with. But the idea here is you can have different intermediate histories, different intermediate universes. You still need multiple universes, but eventually you're kind of fated to end up at the same point. Okay, so there's 3 ways to think about time travel stories. Are we ever going to see any of this? Now, physics, we don't know physics for sure, right? It's experimental science. We keep having revolutions. Excuse me. And maybe what we know about physics will one day be supplanted by something else. But you can pretty much guess that in our domain that we've tested it, we have a pretty good idea of how it works. So I don't think there are going to be any radical revisions to physics that are really going to upend how we think about things. But you can always hope there'll be some little loophole in something we don't really understand, maybe might allow one of these styles of time travel. But depending on which style of time travel logic, you might look to different parts of physics. So for example, if you like this block universe story where it's also one consistent universe, it turns out where you want to look for the possible time travel stories are in this thing, in general relativity, in Einstein's theory of space and time. But if you like the idea of having lots of universes, there's actually something called the many worlds interpretation in quantum mechanics I'll briefly talk about. And if you like this idea that maybe things start out in one place and they end up in that place, but there are lots of different ways to get there, you might look to another aspect of quantum theory called quantum field theory. And then I'm also going to talk about something I study called the retrocausal loophole. That sounds pretty good as far as time travel goes. And I'll tell you what you might make of that. Okay, so let's start with T1. So what does general relativity have to tell us about space and time? Well, first of all, without gravity, if you have flat space-time on one of these space-time diagrams, light can only travel at some speed. So it's, well, the particle at rest is not moving. It's going right through these cones. But what these cones represent is sort of the fastest you can go, right? The angle tells you how fast you're going. And so the fastest you can go is the speed of light. And so these cones sort of define what the geometry of space and time is. What Einstein realizes that gravity can mess up these light cones. And so you have to stay within your light cone, right? You can't go faster than light, so you can only go within your light cones. But in a world where there's gravity, it turns out that space-time is not flat, it's curved. And a light cone in one part is different from a light cone somewhere else. And now, light seems to bend because the light cones aren't oriented with each other, and so sure enough, light bends around massive objects. But you still have to stay within your light cone, but now crazier trajectories are possible, trajectories that would not be possible in flat space-time. And so in the equations of general relativity are cases that, like, for example, if you have a very long, very dense cylinder that's spinning very fast, you can solve the equations to general relativity and discover that these light cones far away are pretty normal, but as you get closer, the light cones tip. It's called frame dragging, and the light cones all tip. And as you get really close, they tip a lot. And as they tip a lot, you might notice here that you could travel, staying within your light cones in a closed loop in space-time, and end up back at the same place and at the same time you started without ever going faster than light in your local frame. And so this is called a closed time-light curve. And they are solutions to general relativity that people have found in the equations. Now, they don't explain how you would solve any of the paradoxes I mentioned, but they're in there. It's in the math. And so you might hope that we could do this, we could travel into our own past. However, many physicists don't like these solutions. They say it's crazy, there has to be some loophole we don't know that eliminates them because they don't want to think about traveling into your own past. And even if you could do it, you just need vast, vast amounts of matter and energy. So it's an engineering problem, but it's an engineering problem with no conceivable solution. An interesting point, though, is that you can't, even if you could build one of these things, you can't travel arbitrarily far back in the past. You could only travel to the past where you had built this closed time-like curve in the first place, because that's where the curve is. You can't travel back to a time before you made the time machine. And so very few movies have to have a receiver. There was one movie, Primer, that was actually in a T2 framework, but at least they had the idea that you have to build the receiver, the back end of the time machine, before you can travel back to it. And so people ask, well, if there's time travel, why aren't they here? Well, maybe we haven't built the receiver, right? Maybe we haven't built the back end of the closed time-like curve. If you're looking to many worlds, you want lots of many worlds, you might have heard this thing called the many worlds interpretation of quantum mechanics. Now, most popular accounts of it are quite off to what the theory actually says. Let me try to give a brief, not totally incorrect view. And basically it starts from looking at the equations of quantum mechanics. And you compute stuff with them, but the stuff you compute doesn't look anything like our universe. You have to then take the things, this big giant mathematical structure that you compute with it, and then make predictions from it, and that can predict things we see in our universe. But a lot of people have looked at the math and said, well, what if this giant crazy mathematical structure is real? And the fact that we're used to compute our universe from it is just a little side detail. And the real reality is this crazy giant mathematical structure that doesn't look anything like space-time. In fact, there's many, many more dimensions than space-time, like crazy number of dimensions, like 3 times the number of particles in the universe, number of dimensions. And so some people say, well, there's this giant dimensional structure in our math, let's take it seriously, and it's just like there's many worlds. And maybe our world is just some tiny weird 4-dimensional slice of this giant piece, but there are there's room for lots of other worlds in there. So that's roughly what the many worlds interpretation is saying. But my majority of physicists, I can't say an overwhelming majority, more and more people are signing up for this, think this is nonsense, myself included. For example, we have similar giant crazy mathematical structures in statistical mechanics and other parts of physics, and nobody looks at those and say, what if those are real too? And I think it's kind of anthropocentric to say, well, I can't predict the outcome of this experiment, so the universe doesn't even know. I mean, if I can't figure it out, surely the universe, there's no way it can decide which one's going to happen. And so if you're interested in my take on that, you can see my essay, The Universe is Not a Computer. Now, even if, of course, this many worlds interpretation is correct, there's still no way to jump universes. So getting a mechanism to get from one universe to the other looks pretty grim. This path integral business, I don't want to spend too much time on it, but you may have heard of this thing called the principle of least time. Where if you want to compute the path that a light ray takes between 2 points, you figure out what path takes the least time, and that happens to be the way the light goes. And it turns out you can put all of classical physics in this sort of 2 endpoint structure, and you look at all the intermediate possibilities and figure out what happens. And you can actually even do quantum physics this way, but when you do quantum physics this way, you have to look at everything that happens in the middle and somehow take all these different paths that happen together and use them to compute the probability that it gets to the endpoint. And so if you take that seriously, which I don't think you should, you might say, well, maybe there are lots of possible intermediate universes between these 2 endpoints, like lots of universes that all are fated to end up at the same point. There's lots of caveats against this here. You can't just say everything happens. That doesn't explain what we see. And now the question is, well, where do you put the endpoint? Where do you have an objective endpoint where everything is going to end up? And that's tied into something called the measurement problem in quantum mechanics. Now, my take, I told you I'd talk about this retrocausal loophole, is that maybe it is possible to interpret the path integral such that one intermediate universe really happens, which would then put us back into the T1 framework, where there'd be one universe. We just don't know which one it is. But to make it work with all the quantum paradoxes, you need retrocausality. You actually need future settings of quantum experiments to affect the secret hidden variables that are going on when you're not looking. And this is definitely out there. This is not the mainstream perspective. But even if I'm right about this retrocausal loophole, you still don't get time travel because you're only causing hidden variables. So the quantum uncertainty principle keeps us from knowing all the details of what's going on. And basically, when you twiddle a knob in an experiment, in the models I'm looking at, you actually would have retrocausal influences in the past, but they would be influences in the very things you couldn't know in the first place. And so you could cause the past, but you could only cause the unknown past. And that will actually solve all these paradoxes and allow you to explain quantum theory, perhaps, but at the expense of not being able to time travel. So if you're interested in the technical version of that, you could try Googling the phrase quantum states as ordinary information. Okay, so the upshot of all this is bad news, I'm afraid. We're not going to get our time travel. If it's going to happen, if somebody told me, look, they discovered time travel, it really works, and proved it to me, I would wager everything I owned that the way they would do it would be via some general relativity loophole, some wormhole, some closed time-like curve. And if so, what does this say about the paradoxes? It's probably the best solution is that, well, maybe some of the things we thought were free choices turned out to not be free choices after all. And of course, the answer I mentioned, where the time travelers, if time travel is ever possible, is that we haven't built the receiver yet. We haven't built the back end of the closed time-like curve, which is why they're not here. Now, you may not like my conclusion here, so if you don't like it, you can take to the streets and complain about it. Thank you very much.
Hey, wake up. There you go. All right. Thank you, Professor Wharton. We'd like to open it up for question and answers. And I know this was a cerebrally shallow topic, so, if you could keep your questions to questions, please, that would speed this along. So who's first? Right here?
Great presentation. The motion aspect, if you did go back in time, where you left is not where you're going to be. The universe is moving, the galaxies are moving, the planets are moving.
Yeah. Okay, so there's this, if you could invent a magical device that would suddenly send you back in time, yes, you have to say back in time where. And very few stories ever deal with the issue that, in some reference frame, most reference frames, the Earth is flying through space. Now, the one story I read that actually took that into account was a book called Timescape by Gregory Benford, where the mechanism was these faster-than-light particles called tachyons. And the idea was they had to send a tachyon beam, so they had to compute where was the Earth going to be in the past in order to make it all work. But typically, that whole issue is ignored, and you imagine that you're in some reference frame fixed on the Earth, and there's only time and there's not space. But of course, time and space are deeply interrelated. So yes, if you're going to build a time machine and it works, come talk to me before you go too far back. And the Earth is somewhere else, and you'll be very sad. Yes.
Got a question for you, Ken.
Yes.
How do you know for sure that I am not a time traveler from the future?
For sure. Well, let's see. You guys talk about this a lot in this. How do you rule out very plausible but extremely implausible events? I guess as a good scientist, I shouldn't rule it out without doing some experiments on you. So I have some equipment I can bring in here.
I have a question. Where does string theory, superstring theory, come into any of this?
So string theory does postulate there are more dimensions, but they're almost always postulated to be extraspatial dimensions. The one point where it would come in is there are tiny little bits of string theory where people play around with adding an extra time dimension, adding 2 time dimensions, at which point a lot of these logical fallacies maybe aren't fallacies at all. Maybe you can have two time dimensions, and you can travel in one with respect to the other. There's been very, very little work done on two time dimensional theories, and certainly not enough to say anything. But that would be the entry point. String theories with two time dimensions could be interesting from that perspective.
Yeah, I have a question. So, growing up, I have learned a definition of time that I really does not set well with me, and that is that some element has a frequency, and if you put it in a spacecraft or a plane and orbited around the Earth, the frequency slows down relative to the same element that's placed on Earth.
Okay, right.
So to me, can you define, is that the correct definition, one?
Well, that's a great definition of
but secondly,
okay.
That's like saying, if I take my watch, that's my timekeeping device, and if I put it in molasses, it slows down, so time slows down. If I slam it against the cement, it breaks, so time has stopped. I mean, you're manipulating the timekeeping device in my mind. So do we have a better definition?
Okay, so there's what is time, and when people ask what is time, you should definitely think in terms of space. If you understand space, then that same kind of thing is time. But if you're asking about what is a meter, or what is a second, that's a different question entirely. If you're asking about seconds, now you can start talking about clocks. You can talk about what's used to measure time. And the difference between putting a clock in molasses and taking a clock on a spaceship, and they've done this, they've sent clocks in rocket ships and they come back slower, is that for the relativistic case, every conceivable timekeeping device, biological aging, light bouncing back and forth between two mirrors, a Rolex, a digital watch, it doesn't matter. All of them are going to slow by the same amount. While the molasses example, you might have a molasses-proof watch that doesn't slow by the same amount. So it's a little different in that it's every conceivable way you can think of measuring time is slowed all together. And so it really is slowing relative to the one on Earth. Of course, the weird thing about it is if you're in the spaceship, you think the one on Earth is slowed until you get back. Actually, you have to accelerate to get back, right? And then you discover that the one that accelerated is the one that really did age less. But if there's no acceleration, they both think the other one's going slower, and they're both right.
There was one diagram that you made where there was time going along, and then you split off another universe.
Doc Brown's diagram on the chalkboard. Okay, yeah.
Well, what was going on with that universe before you did the splitting?
Well, you see, the flux capacitor.
Did it create? No, I mean, but was there supposed? Well, but was there supposed to have been that other universe before the split?
That's a very good question. So there are different ways to do it. You can imagine that you create the universe by splitting. Some people imagine that. You can imagine the universe is always there. Typically, I think you imagine you create the universe by time traveling. But there are lots of logically coherent ways to think about it. I think the most natural way to think about it is that the universe is always there, and you were just jumping into it. But from a story perspective, then you have this worry about, well, what happened to all those other characters? I mean, here's an example of things you can get into with that. So you can think about Back to the Future, the original, not the sequel. And you say, well, is this a T1 or a T2 story? And the genius of the end is it seems like it's a T1 story, because when Marty McFly comes back at the end, he sees himself drive off in the DeLorean from earlier in the movie. And you say, it's all one big self-consistent universe. But then the big reveal is he goes home and he wakes up and discovers that he's in a totally different universe, right? He's in this better universe where his family is happier and everything's better. And so that's all great. But then you think back to that first scene. You say, well, what was going on in that first scene if we're in a T2 universe? The Marty he sees driving away wasn't him. That was the Marty who had the really good life, who had lived in this happy family. And so he ended up in the time machine. So he's a totally different person, this other Marty. It's not him. It's Marty from the other universe. And so maybe they should have written a sequel talking about what happened to the other Marty. I don't know.
Quick question. As you know, the multi-worlds interpretation comes about from certain paradoxes in quantum mechanics that they use the multi-worlds universe to explain. How do you explain it? Because quantum mechanics is just bizarre. So without the multi-worlds process, how do you explain them?
quantum mechanics is very bizarre. Now, the many worlds process is basically taking the math of quantum mechanics that was already there, literally. Basically, you believe it. You believe the math. And so everything that the many worlds can explain can be explained in any interpretation of the math. So these are just different interpretations of the same math. Is the stuff in the math real, or is it just something I use to compute probabilities? Whichever way you take it, you can still compute the same things. Now, I am very deeply interested in how to explain quantum phenomena. And one thing I didn't mention that is relevant to all this is that all the microscopic phenomena that we know of are time-symmetric. Now, you take a little movie of two particles crashing into each other, or light doing something or other with atoms, you play it backwards, and it still obeys the laws of physics. So we have this nice, beautiful symmetry where everything looks nice and symmetric on a microscopic scale, which is really interesting to me. It's not the time we experience in the macroscopic world. And so what I'm looking for are actually time-symmetric interpretations of what's going on down there. And the many worlds story, the idea that sort of these many worlds are well, that's the standard version of it, that's the popular version of it, that many worlds are kind of popping into existence. If you run that backward, all these worlds are actually converging. It's not as time-symmetric as I would like. So I'm looking for a story where it has, as I mentioned, it has these retrocausal elements where, yeah, we expect if we turn a knob, something in the immediate future to respond to it. We don't expect if we turn a knob, something in the immediate past responding to it. If it did respond, that would be weird. And we argue that quantum mechanics is weird in exactly that way.
So, question about the conclusion. You said that because there are multiple worlds, and yes, hopping between worlds is an explanation of kind of how time travel really exists, but it doesn't really happen within the same world. In the same way, there are parts of each world that actually do coincide. It's like a movie where you have, or when you edit, right? You create versions of it, and you kind of cut things out. But some parts of it does align, does kind of exist in both worlds. Isn't time travel then defined as how these things align together?
Okay, if we're just talking about just a bunch of classical universes, and some things are the same and some things are different, I guess if you're focusing on what's the same, then presumably when you jump from one universe to the other, to keep it the same as possible, you would end up at the same time in the second universe that you started in the first. So right away, the idea of going earlier in one is kind of looking to what's different rather than looking to what's the same. But when you go into the math of quantum theory and look at the many worlds story, it's actually very hard to parse out, well, which one is our world? In fact, this is one of the deep problems in many worlds story. You have this giant mathematical structure, and finding something in it that looks like our world is kind of tricky and arbitrary and subjective. And there's not a fine line between, oh, here's one universe and here's the other. It's all this big mishmash. And people are still trying to make sense of, can you even talk about probabilities in such a universe, in such a multiverse? There are all these universes where the laws of quantum mechanics don't work. And why aren't we in one of those? Yeah, so all sorts of interesting issues.
Hi there. You touched on something a little while ago that might actually be real. I'm not sure that the time travel stuff is, but you touched on something and then just blew past it. But ever since I first saw the equations of special relativity, I've had that problem with the two clocks running slower.
Mm-hmm.
You said that even if you're in the spaceship going out,
Mm-hmm.
it looks like the other guy's clock you left behind is going slower. Or let's say you have two spaceships passing
Right.
each other going opposite directions
Right.
in space. The other guy's clock looks slower.
Right. The other guy's clock is slower.
I can't, okay. How?
It's hard. It's tricky.
Is there any way you can help me
Yes.
get my head around that
Yeah,
one?
so the reason it's hard to wrap your head around it is we all have this idea of now. And we have this idea that now is meaningful. Now, and not just like now as opposed to now, not that kind of meaningful. I mean the idea that my now and the instant I'm experiencing now, there's some special instant on the other side of the universe or the distant clock that's important. But relativity tells us that now is subjective. I mean, not just that all nows are equally special. That's obvious, I hope. But the idea that there's this line of simultaneousness, that's a fiction. And different observers see different lines of simultaneousness. And the reason that you can have two clocks both thinking the other one's going slower is they're using different lines of simultaneity to say, what's that other clock doing right now? They mean different things. And that's the root of the problem. That's the root of why it's so hard to think about it. It's because we like to think there is this global now that really is meaningful. But there is no global now. There are only subjective nows. So in order to compare two clocks objectively, you have to compare them at 2 times. If they're passing by each other, you can only compare them at 1 time. Okay? In order for them to compare the second time, one of them or both have to accelerate. And then that changes it. And then the one that accelerates the most ages less. Acceleration is objective.
I have a question. You mentioned Richard Feynman earlier. Didn't he have in his equations for like protons turning into different particles, didn't he have an arrow for time? And he said it would work both ways?
He liked to imagine these scenarios where particles would go back in time and then go forward. And as I mentioned, that logic doesn't even make sense. What does it mean to go back in time? If you have this block universe, it has a S curve in it, which is how he imagined it, and you just play it, then you have one particle, suddenly you get to the bottom of the S, and now you have 3 particles, and then 2 of them merge into each other, disappear, and now you have 1 particle. And that's kind of how he thought of it. In fact, he got the example from the story of a bombardier flying over a switchback, and looking down, seeing 1 road, and suddenly seeing 3 roads, and then seeing 1 road. And that was the inspiration for, he called his bombardier example. And that's probably a much better way to think about it than as a particle changing direction in time and going back. Nonetheless, he had interesting physical insights from the idea that particles could change direction. He was very careful not to actually use that language, I hope, because it's not good language to talk about things going backward in time.
The one thing I'm absolutely sure of is that I feel more like the way I feel now than the way I felt yesterday. And I worked that out in group therapy, so, you know, that's one way to get over a lot of this stuff if you people are flopping around with this.
I wrote a poem about this recently. When I've been just anywhere, I said I'm here when I was there. When I've been just any when, I've thought I'm now when I was then. And here's not special anyhow, so surely there's no special now. I don't know, I posted it on Facebook. I can't remember what I called it. Against the here and now, maybe.
First of all, I'd just like to say that I can prove that Joel is not a time traveler. Okay.
Okay, let's hear it. Let's hear the
he
proof.
Was standing in line for food earlier, and he told me that last week he did not bet on the Buckeyes, Ohio State, to win the national championship. And if he was a time traveler, he would have made that bet. Secondly, I have your Tipler cylinders that create the circular time travel possibility. To me, in a layman's term, that sounds an awful lot like something called a black hole. I mean, something that's spinning really fast and sucks in and affects the ability of light to move. Now, my understanding is that you can't get anything good back out of a black hole if you throw it in there. So maybe the problem with building a Tipler cylinder is that if anything you get close to it is going to turn into garbage, and thus it's not you can send quarks back to a previous time, but you can't send you back to a previous time.
Maybe. There are lots of people that were looking for such loopholes to prevent any paradoxes from happening. But it's true that around a black hole, spinning black hole, you also get closed time-like curves, or you can find solutions in the math. Whether or not they really exist, it's unclear. Those solutions have to pass back out of the event horizon of the black hole, but it seems on paper to actually be okay. It's really tricky stuff to interpret the math. It's bad enough interpreting quantum math. Actually, that's worse. But interpreting these solutions and saying, well, what would happen? It's really interesting exercise.
Edge of Tomorrow, Groundhog Day, what is that, T1 or T2?
Groundhog Day had to be T2. I mean, every day was a new universe, right? Yeah, Groundhog Day. Well, the first one you mentioned, or? Oh, The Edge of Tomorrow. Well, that's the same kind of thing, right? That's Groundhog Day in space, I heard. Okay, yeah. Let's see, which Doctor Who? Yeah, that's like saying, what about Star Trek, right? That's they haven't made a careful effort to keep it all consistent. So anything without the really careful effort to keep it all consistent is T2. Yeah.
Is the universe flat?
I don't have a horse in that race, but from all the data, it seems to be a nice globally asymptotically flat universe. Sure, but this idea that right now the universe is accelerating. We don't know why. And so people say, well, we don't know why, but it's always going to keep accelerating. It's going to keep accelerating more and more. But since we don't know why it's accelerating, we don't really know it's not going to change. Until we really understand why is it accelerating, we can't really predict what it's going to keep doing. You can extrapolate, but it's kind of a guess to see what's going to happen.
Okay, we have 2 more questions.
An accelerated field, affects time, and a gravitational field affects time the same way, and that there's a relationship between gravity and acceleration.
Right.
And maybe you could explain that a little bit. And also, with space itself expanding, does that count as acceleration, or does it not? If you're just riding along with space.
Okay, so the first question was just mentioning that not only can you change the speed of clocks with velocity, relative velocity, but you can also change it with relative gravitational field. So a clock at a mountaintop is going to tick at a slightly different rate than a clock at sea level. And that's just another way in which time is relative at different points in our universe. It's an interesting question about the accelerating universe and whether that counts as real acceleration. So at our scale, certainly not, because even if there's this infinitesimal expansion of the space in an atom in my body, the restoring force between that restores the size of the atom immediately pops back to what the old size was. So whether or not, and the same thing is true in our solar system and even our galaxy. So really, the only place that space is filling in is sort of between clusters of galaxies. But whether or not that counts as as a very, very small acceleration for some physical purpose, that's an interesting question. I don't know the answer.
So I'm going to take the opportunity, because I have the mic, to ask the last question. I'm going to throw out a phrase, and you tell me what it means, because I don't. Is quantum tunneling, in effect, traveling forward in time?
So quantum tunneling is getting more and more important as they get transistors smaller and smaller on a computer chip, in that you can have this seemingly insurmountable barrier that an electron can nonetheless seem to find itself on the other side of. Even though it didn't have enough energy to get over it, it did somehow find itself through it. And the interesting time question to tunneling is you calculate how long did it take the electron to tunnel through. And the equations give you an imaginary number. So then you say, well, let's do an experiment. And you send a pulse, and you send it through something, or it basically has to quantum tunnel through. And suddenly it comes out and it looks like it's traveling faster than light, as if it didn't take any time at all to get through there. And so they do these experiments. Now the problem is, to do that, you lose a lot of intensity. And so what was the middle of your laser pulse stays in middle. But if you just measure the time from the leading edge of your laser pulse, it's not going faster than light. But if you measure from the middle of your laser pulse, it is going faster than light. So there's all this debate about, well, is it really going faster than light or not? And most people are pretty happy with it not going faster than light. But if you could go faster than light, there's a way to go back in time. So maybe I'll leave it at that.
All right. Please thank Professor Wharton. Thank you.